In this video, I'm going to explain how you might discover a method to find the area or volume below a graph in a way that isn't shown nearly as much as other methods, but is the approach used to prove an extremely important theorem, that a function is Riemann integrable if it is bounded and discontinuous at a finite number of points. My goal here isn't to get into all the technical details and rigor, but rather to explain the method in a way where you come away feeling like you could have discovered it yourself, given enough time and the proper insights. This means in some places we're going to make some assumptions that are unnecessary for reaching the final conclusions in order to simplify the math down a bit. But in light of this video's spirit, mathematical discoveries almost always start with specific examples and lots of assumptions to make the problem easier to tackle. It isn't until after initially playing around with an idea and gaining some insight that generalizations are made. So, let's see our first problem. Suppose you're pondering the idea of how to find the area beneath a curve on some interval, let's say from x equals 0 to x equals 1. To make the graph of this curve f of x behave nicely, we'll start by assuming three things about it on this interval. 1. That it lies entirely on or above the x-axis, never below. 2. That it stays bounded, never shooting off to infinity. And 3. That it's continuous, so there won't be any breaks or sudden jumps in it. I'll note here that only the boundedness condition is necessary. The other two are just here for simplification. One idea you might have is to first approximate the area and hope that along the way you'll be able to make some refinements to better that approximation, eventually leading you to the exact area. One way to do this is to partition this interval from 0 to 1 into many different subintervals, and to make things as easy as possible for ourselves, each can be of the same length. If we split it up into n equally length subintervals, then each one will be of length 1 over n. If we can approximate the area below the curve in each one of these subintervals, then it would make sense that adding them all up approximates the area over the entire interval. Now, let's focus our attention on an arbitrary one of these subintervals, the one from I over n to I plus 1 over n. We know the area of a rectangle can be easily calculated, it's just base times height. So rectangles seem like a reasonable way to approximate the area for each subinterval. Notice that if we take the height of the rectangle to be the maximum point of f on this subinterval, then the area of the rectangle approximation overestimates the actual area below the curve. This extra area comes from parts that are in the rectangle but above f. Here I'm using the supremum to keep the notation consistent with what you'll see in other places, but since we're assuming continuity, the supremum and maximum will be the same. Do this for every subinterval and sum up all their areas, and our total approximation will overestimate the total area below the curve from 0 to 1. We use the notation u of f p to mean the upper sum of f with partition p. Now, if we choose the height of the rectangle to be the minimum point of f on each subinterval, then the rectangle approximation for the area will underestimate the actual area, as seen by parts below f but above the rectangle. For the same reasons as before, I'm using the notation for infimum, which is the same as the minimum in our case. Do this for every subinterval and sum up all their areas, and our total approximation will underestimate the total area below the curve from 0 to 1. Here, L of fp means the lower sum of f with partition p. So the actual area we seek is squeezed between our lower sum and our upper sum. From here, a natural question to ask is what happens to these two approximations as we increase the number of subintervals n. First, let's consider what happens to our upper sum as this happens. If we take the same arbitrary subinterval as before and split it in half, we see that as the subinterval lengths decrease and the number of subintervals increase, the area of our upper rectangle approximation decreases. You can see this because the two thinner rectangles don't completely fill up the blue rectangle, as there's still blue left that's not in the two thinner ones. For the lower rectangle approximation, as the subinterval lengths decrease and the number of subintervals increase, the area approximation increases. This is seen by the extra transparent area that's part of the thinner rectangles, but not part of the original rectangle. So the upper sums are decreasing, and the lower sums are increasing. Now, what happens if they converge to the same limit? Well, since the actual area is bounded between our two approximations, if the lower and upper sums converge to the same limit, then that limit must be precisely the actual area. So, we have discovered the following. The lower and upper area approximations, called the lower and upper Darboux sums respectively, bound the area beneath f of x from below and from above. If both these sums converge to the same limit L, then that limit equals the area bounded between f and the x-axis, and we call this the integral from 0 to 1 of f of x dx. When this is the case, we also say that f is Darboux integrable, or equivalently, that f is Riemann integrable. So, now that we have discovered Darboux integration for a single variable function, we can try to see if a similar result would make sense for a multivariable function, f of x, y, in three-dimensional space. We'll make an analogous set of assumptions here, so the 3D surface will be non-negative, bounded, and continuous. Instead of finding the area over a one-dimensional interval along the x-axis, the volume we want to find will be over a two-dimensional rectangle in the xy plane. Let's say that this region R in the xy plane runs from 0 to 1 along both the x and y axes. Similarly to how we partitioned the x-axis and used rectangles to approximate the area in the 2D case, in this 3D case, we'll partition the x and y axes and use cuboids to approximate the volume. We can partition the x-axis into m equally lengthed subintervals and the y-axis into n equally lengthed subintervals. Now, consider an arbitrary subrectangle that goes from I over m to I plus 1 over m in the x direction, and j over n to j plus 1 over n in the y direction. That subrectangle will be shaded green. If we take the height of the cuboid to be the maximum value of f on this subrectangle, then its volume will be greater than the actual volume below f over this region. If we do this for every subrectangle in R, then our total approximation will overestimate the volume beneath the function. Similarly, choosing the height of the cuboid to be the minimum value of f on this subrectangle results in a volume that is less than the actual area below f over this region. If we do this for every subrectangle in R, then our total approximation underestimates the volume beneath the function. So the actual volume bounded by R and f is squeezed between the upper sum and the lower sum. Just like before, we'll now observe what happens as m and n increase. Put another way, as the area of each of the subrectangles decreases, and the number of subrectangles in R increases. If we take the same arbitrary subrectangle and split it in half along both the x and y directions, the volume of the upper cuboid approximation decreases. This is because the 4 purple cuboids take up less volume than the 1 blue cuboid. And for the lower cuboid approximation, the volume increases as the number of subrectangles increase. You can see this from the fact that the orange volume completely encloses the red volume, and it also contains extra that is not part of the red. This is analogous to what happened in the 2D case. The actual volume is bounded above by the upper sum and below by the lower sum. The upper sum is decreasing, and the lower sum is increasing. So if the upper and lower sums converge to the same number, then that number must be precisely the volume between f and R. We write this as the double integral over R of f of xy dA and say that f is Darboux and Riemann integrable. Now that we see how Darboux sums in integration are defined for 2 and 3 dimensions, you might wonder if this can be generalized to 4 or 5 dimensions, or any natural number of dimensions. In fact, they can, but to do that you have to leave the realm of visual intuition and physical interpretations of the integral in order to generalize the integral as a more abstract mathematical object. What would n-nested integrals represent physically? Other than an n+1 dimensional hypervolume or the mass of some n-dimensional object, it's hard to come up with any reasonable physical interpretation of them. And while we're on the topic of generalizations, if whenever you're exploring a mathematical idea, you come to some conclusion or result, see if you can go back through your process and look for any place where you made a specific choice that could be made more general. As an example of this, our choice to use rectangles or cuboids to approximate the integral was arbitrarily made for the simplicity of computing their areas and volumes. Nothing about our process or result was contingent on their use. It would make sense that any two sequences that appropriately bound the integral and become equal in the limit should equal the value of the integral, not just the sequences of our upper and lower rectangle or cuboid approximations.